Mary?
No, sir.
Okay. Let's start new chapter, that is Kinetic Theory of Gas, which is similar to or quite similar topic related to this last chapter, thermodynamics. Kinetic Theory of Gas, or simply KTG, in which you have to define three main derivation. First is pressure exerted by gas at molecular level. Second is kinetic interpretation and calculation of specific heat, internal energy for mixture of gas. And third is definition of velocity of gas for various different terms. So for first part, pressure exerted by gas, let me define you property of ideal gas. Property of ideal gas. First is, in last chapter I had defined you difference between real gas and ideal gas. So for ideal gas, there will be no interaction of particle, or there will be no interaction between particles. First is, if there is no interaction between particle, it moves with same velocity along all coordinate axes. It moves with same velocity along all coordinate axis, that is Vx, Vy, and Vz all are equal to each other. Third, it always makes elastic collision, whether with its neighboring particle or with the wall of container. It makes elastic collision with neighboring particle as well as wall of container. Okay, just write it down till this. Safullah, written?
1 minute. Yes, I finished.
Now, related to this concept, you have to first derive pressure exerted by ideal gas. In fluid, we have defined pressure exerted by a fluid. That pressure was due to acceleration of fluid by gravity. But in this part, we have to calculate pressure exerted due to its thermal movement or its thermal kinetic energy at molecular level. So suppose there is a cube of side L. This is x-axis, y-axis, and z-axis. Consider a cubical vessel of side L containing an gaseous particle each of mass m, moving at so this is L. Let's say there is a particle at this point which is going along this direction at some initial velocity Vx. Mass of this particular gas particle is m. So on hitting this surface, it may get returned along this direction. And since collision between any two particles or a wall of container will be always elastic, so it will again get the same velocity Vx along this direction. So if you have to calculate net change in linear momentum during this collision, so first, change in linear momentum during this collision will be P final minus P initial. Final momentum is the downward part, which is going along positive x-axis. So it will be mvx. Initial momentum is the upper part, which is going along negative coordinate x-axis. So it will be minus of mvx. So minus minus cancel out. So it will be 2 times of mvx. Is it clear?
Yes.
Okay, just write it until this. Safrullah, done?
Yes, sir.
Okay. So we have just calculated change in linear momentum during this collision. So if you have to calculate how much time it is taking for this particular process. So time taken, it will be distance traveled by speed of that particular particle. So it is going from one end to the other end and then returning back. So the total distance is 2L divided by speed Vx. So this much amount of time it will take for this particular change in its linear momentum. So we have change in linear momentum as well as time taken. So according to second law, we can say force exerted equals to change in linear momentum by time taken. Change in linear momentum we have 2 times of mvx by time taken 2 times of L divided by Vx. So 2 and 2 cancel out, mvx squared divided by L. Mehreen, is it clear?
Yes, sir.
Tell me the formula of pressure, Mehreen. Pressure equals to Safullah.
Force by area.
Good. So it will be force exerted by area of cross section. So this one particle falling on wall may have exerted this much amount of force divided by L. Now, if I suppose this particular system containing n number of particles, so total force will be n times of this, and the area of that wall on which it is striking is square in shape, so its area will be L squared. So this is total area of that surface and n, since we have n number of particles. So number of particles multiplied by its mass will be total mass. Length and L square will be L cube times Vx squared. So P is equals to mass, L cube is volume, Vx squared. Mass by volume is also called density, so rho times Vx squared. Now we have to convert this particular velocity in some other form. Let me define you. Now, since Vx, Vy, Vz all are equal to each other, and in terms of, suppose you have V in vector form, so you will write Vx I cap, Vy j cap, and Vz k cap. So you have to calculate, suppose, magnitude of this velocity. So magnitude of velocity will be root under Vx square, Vy square, Vz square. Since all are equal, so we can say 3 times of Vx square. On squaring both sides, this magnitude will be averaged over whole term. So it will be V bar square equals to 3 times of Vx square. So Vx square will be 1/3 of V bar square. Now put this value in the above expression. Hence, pressure exerted will be rho. Vx is 1/3 of V bar. So it will be 1/3 rho V bar squared. So this will be your final expression of pressure exerted by ideal gas. Memuna, any doubt?
No, sir.
Okay, just write it down. Safullah, done?
Yes, sir.
Any doubt till this part?
No, sir.
No, sir.
Okay, let's stop here for today. In next class, we'll continue further. Okay. Abdul Wahid, be there. I'm coming. Okay. The rest of you, you may leave.
Thank you, sir.
Thank
Thank you,
you.
sir.
Thank you, sir.
Thank you.
Sir, am I going to be in the same tuition?
Yes, Mehreen?
Sir, am I going to be in the same tuition, same classes?
Yeah.
So when are you going to teach me fluids and
After completing this, okay. From next class onward, I will I will convey any message through any nishkarsas to you. Okay.
Okay, sir.
Okay.
Thank you, sir.
Thank you. Yes, Abdul Wahid. Have you prepared? Which topic? Yesterday's topic, that is heat engine, adiabatic process.